Hello and thank you for joining me for another ITY video with top Australian and international executives. Today I have with me Dr. Joanna Batstone, Vice President and Lab Director of IBM Research Australia and also the CTO. Welcome to the program.
Thank you.
So you were one of the closing keynote speakers today at CeBIT Australia 2016. Can you please just give us the title and I mean we're talking about your keynote, but what was the title and the brief version of what you spoke about today? And we'll go into more detail in just a moment.
So the title of my talk was The Cognitive Computing Comes of Age, and it was a dialogue around how we're transforming from a discussion around big data and analytics into the new cognitive era.
So that's probably the best place to start. What is the definition of cognitive computing, and when was this new era announced?
So we announced the new cognitive era last October.
Very fresh then?
Ginny Rometty announced this last year, actually. And for us, it's a new model of programming. If you think back to the 1900s and the Industrial Revolution, and as we entered the 20th century, we're in a computational world of, in essence, tabulating machines.
Sure.
With the invention of the vacuum tube and the transistor, we've moved into the world of what we think of as computing today, programmable systems, primarily based on von Neumann architecture, programmable systems. But as we look now at the huge amounts of data that we have to manage across industry, then we need new methods and models of analyzing those data sets. And that brings us to the cognitive era, where we need to be able to build systems that not just analyze data, but can learn from the data, learn patterns in the data, can reason with the information in the data sets, and actually systems that can interact naturally with human beings. And that drives a fundamentally different way of interacting with systems and the way we think about programming systems and the way that we can build systems to transform industries.
So is this the same as artificial intelligence, or is this a new form of augmented intelligence?
We like to use the term augmented intelligence, or often accessible intelligence. Much of the technology comes from the field of artificial intelligence, but the word artificial somehow implies fake or not real.
Yeah, that's right.
Whereas these are real systems that are making a difference in real world applications like healthcare. So we like to use the expression augmented intelligence. The fundamental technologies of algorithms and machine learning and deep learning come from the field and scientific discipline of artificial intelligence, but the application of them to practical real world examples is augmented intelligence.
Sure. And I would imagine that all of this is being done with digital technology, the zeros and ones that are processors and transistors, everything else works on. So surely all the developments in quantum technology is going to take this cognitive era and put it on steroids. I mean, you must be working on that in a massive way.
So there's a couple of interesting thoughts there. Binary systems, zeros and ones, clearly we can do a lot today with cognitive systems using conventional computer architectures. But there are two other very interesting different approaches to how we can build new computer architectures of the future. One is called quantum computing,
which is all the shades of grey in between 0 and 1.
All the shades of grey between 0 and 1, and the predictability of is it 1 or a 0. It's a quantum state, not a binary state. Huge advances in quantum computing and the ability actually to implement 9-qubit systems based on conventional silicon. So lots of interesting research, and within IBM we do a lot of research in quantum.
Which we're still yet to truly break through or understand. We're still not quite there. I mean, perhaps in the labs you're way advanced.
So in the labs there's a lot of interesting new applications and implementation of quantum systems. But the other interesting example of new architectures is something that we call neuromorphic technologies. So
sounds like a blend between neurons and processors.
So the way information flow happens in the brain, right? It's information flow. Your synapses are firing. There's information that's being transmitted within the brain. So what if we could design a computer architecture
to work like that?
That works like that. Data in, data out, functions the way it does in the human brain. So we've been building a system like that. We call it True North. But it's an example of neuromorphic computing, which is the next generation of where cognitive will go in the future.
Didn't the sci-fi writers call it cybernetic computing? But neuromorphic sounds pretty good to me. So this all sort of, I mean, the big buzzword of the moment is big data. It's been a big buzzword for a long time, but what we think of as big data or data today must have changed over the past few years. What does it look like today in 2016? Where will it be in the next few years, and how is cognitive computing helping us manage all of this big data in a much more efficient and effective manner?
We've been talking about big data probably for at least a decade. But the interesting thing today in 2016 is 90% of the data that we process and try to manage and interpret today was created in the last 24 months.
Yeah, very recent.
That's huge.
Yeah.
And it's being driven by a rapid explosion in social media data, in video data, in sensor data.
Biometric data, everything.
Biometrics data, the devices we're wearing on our arms to monitor our physical health and well-being. So the amount of data is exploding, and it's far beyond what conventional humans or computer systems of today can manage, and hence you need to look at new approaches for interpreting data, and hence cognitive.
And so that's obviously one of the ways that humans can better deal with this data. But I mean, are we all going to need like a little personal Watson, perhaps embedded in our brains to deal with it? Or I mean, and tell us about Watson. Is it now all cloud-based? Was there originally a single machine? But there's two questions there. I know. Sorry.
So Watson originally, right? The machine that we built to play the game of
Jeopardy,
right,
famously.
was a series of servers implemented actually in our IBM research labs in Yorktown Heights, New York.
And that would have been before the cloud as we know it existed.
Before the cloud as we think of it today existed. So the research project, I was actually a part of that team in New York back in 2006, was very much around designing this natural mode of interaction between computer and human with a focus on natural language understanding. So it was at the time a system of systems
but still,
in a data center.
Yeah, but still sort of one giant computer sitting in a data center as such, sort of.
So think of it in essence as one API.
Yeah.
We built an API that was really good at questions and answering questions. Think of that as one API.
Yeah.
Watson today is delivered as a series of cloud-based services. We have a Watson Developer Cloud that runs on Bluemix in our cloud data centers. It all runs on SoftLayer, but it's a cloud.
Yeah.
And so we deliver services, Watson APIs, now as services in the cloud. And business partners and clients build new services based on our cloud Watson platform.
And do Watson and True North get along, or are they not friends yet?
So think of True North as a specialized architecture that will be really good at accelerating certain styles of function. True North, as a neuromorphic system, is good at pattern recognition. So if you're thinking about your ability to do video analytics, True North can be thought of as an accelerator to be specialized around a certain set of APIs. It's not general purpose compute.
Sure. Not yet anyway.
Not yet anyway.
One day, yes. So this also leads me to another major buzzword, which people can probably predict, the Internet of Things. How does all of this blend into the reality of cognitive computing, which you spoke about during your keynote, which I will have for people to be able to watch as with this video?
So the Internet of Things is really interesting because it's exploding into our everyday life. And it's driven by the fact that we can connect anything and everything, whether it's our washing machine or the drone that's flying over a field, or the information, sensors in the house, sensors in the wall, temperature, humidity, smart buildings. Sensors are everywhere. Because of that, it's driving huge amounts of data. And back to the original argument, there's so much data, you need different styles of compute technology to do immediate, instantaneous pattern recognition, identification in the data, often at point of origin. So the Internet of Things is in fact a marriage of computation at the edge of the network with computation in the cloud, and it's a symbiotic relationship. Sometimes you do the compute in the cloud, sometimes you'll do it at the edge of the network. But the Internet of Things, I think, is the next wave it's the next wave that will drive advances in cognitive technologies.
Now, one of the other things that people have spoken about with the Internet of Things is the Internet of Hackable Things, and how there's a lot of security issues. Will cognitive computing give the Internet of Things the brains to know it's being hacked and to sort of proactively protect itself? I mean, obviously it'll still need programming from humans, but can we rely upon technology to help protect us from technology or other hackers?
Yeah, so security and privacy comes up a lot of the time, right?
It's a huge issue. Everyone's
encryption,
scared.
homomorphic encryption.
Minecraft today was hacked. It's millions of usernames and passwords are out there. So it's a non-stop thing.
So within the world of the Internet of Things, you have to be able to protect the data, and there are new technologies. Homomorphic encryption is one of those.
I mean, not just the data, but the devices themselves, so they don't turn up the sensors and blow up in your house, or turn your fridge off and defrost all your food. But sorry, keep going.
So the world of technology is going to require us to protect, from a security perspective, the sensors and networks that we drive. So new encryption techniques emerge. Homomorphic encryption is one of those. And so clearly it's going to drive a different level of acceleration in our investment in security and privacy.
And are you working on these things in the labs?
We're not in Australia. In our research lab in Australia, we have a very active Australia development lab in the Gold Coast with a focus on security. And we have our research labs in New York and Zurich that specialize in security and privacy research.
And there was a couple of stats I got out of your keynote, which was that each person will generate 1 million gigabytes of health-related data in their lifetime, equivalent to 300 million books, and also that the price of not understanding all of this can be extreme. And what is the risk of us not understanding all the insights from these data sets? So what did you want to say to those?
From a healthcare perspective, right? One of the challenges with all of this data, 300 million books per person. How, as a clinician, can you deliver personalized healthcare treatment? And so that's really a perfect example of an application of cognitive technologies, that we can bring all of those data sets together and enable physicians to drive new insights on data and hence deliver personalized treatment for you based on your genetic profile.
Sure. And then the dangers of not understanding, or the price of not understanding all of this, it can be extreme. Just elaborate a little bit on that.
So one of the projects that we have going on right now is looking at skin cancer and leveraging medical imaging to identify early evidence of skin cancer.
Which must also be a form of pattern recognition as well.
It's an example of pattern recognition. So early detection and hence early treatment is one of the best ways to save people's lives.
And with the medical stuff, you were just mentioning how you can have personalized medical care, but that also would lead into cognitive computing helping to deliver personalized education for students. And you gave some examples in the keynote as well.
Yeah, so think about as we're growing up as children, our ability to learn changes. It changes each year. We as individuals, we learn in different ways and different styles of learning. So as we partner with Sesame Workshop, we're looking at doing the research that shows how children learn and then can provide personalized educational assistance to the children. So imagine hundreds of children in an elementary school. They all have different learning styles. We can deliver now personalized education tailored to your learning style or to mine.
Look forward to that happening. So just last couple of questions. What's the best piece of advice you've ever received to help you get where you are today?
So I started life as a research physicist, and so there are many different directions that you could take as a young graduate student. And one of the pieces of advice I was given was, whatever you do something that really matters. And so I've always followed that, right? So to find a project that feels important and matters from a society and an impact perspective. And then a second piece of advice, if you're not sure what to do something.
Yeah.
It's better to do something and start with a piece of research than to sit back and wait. So those two are the two pieces of advice.
Excellent. Thank you for sharing. And do you have any final thoughts you'd like to share with IT Wire viewers and readers and for the future cognitive thinkers of the world?
For the future cognitive thinkers of the world, it's really going to be a transformation journey. It's going to change the way we teach students. It's going to change the way we teach university students, programming models of the future. But it's going to change the way business and IT come together to transform business.
Dr. Batstone, thank you very much for your time.
You're welcome.
Thank you.
Thank you.